All right, guys, so as we wrap up 5.3 and our talk about definite integrals and antiderivatives, we're going to go into that exact term, antiderivatives. Before we do so, we're going to start making some connections between differential and integral calculus. So what this means is basically connecting the dots between derivatives and integrals, okay? Antiderivatives, that's not the first time that we've heard this term. We've talked about antiderivatives. We give it a very basic definition as being basically the opposite or the step before the derivative. So you take the derivative and now you have a derivative. What do you do to go from derivative back up to the original function? And really, that's what the integral is. It is the antiderivative. It's kind of the opposite of what we know about derivatives. The integral is the derivative and function kind of all meshed together. And so what we're going to use real quick is reintroduce the antiderivative in terms of integrals now, okay? So we've heard that antiderivative term before. And so what we see between the integrals and the derivative is this exact statement. So the true connection is that if I took the derivative of the integral, all right, I'm sorry, this is not a, this is not b this time, this is x. All right, if I took our derivative of our particular function that we are dealing with, all right, and let's make sure I identify these right, because I don't want to get confused as to which ones that we're dealing with. We'll call f of t. If I'm using x up there, I don't want to mix and match. But if I'm taking the derivative of this integral, what this gives me in return is my original function f. So that's what we mean when we say almost the opposite. What happened the step before the derivative was taken, all right? And so that leads us into what we call the antiderivative, okay? So we're going to say let capital F be the antiderivative, okay? So let F be the antiderivative of little f. Then what we can say is that from a to x, and again, we're using these values or these variables because we don't want to get a mix and match between the f of x and which ones we actually are concerned with. So a of f, we'll call it t again, dt, equals the antiderivative of f of x. Whoops, I put of t, I mean of x. Of x, and then don't forget plus your constant c. All right, so this is what we talked about before. When we find that opposite, that step before, we have to add that constant in there of antiderivatives, because what if there was a constant that and the derivative was 0, right? So it's always a possibility. All right, so let's take a look here as we continue to move a little bit further on into it, okay? So now we have some constant c. Now, throwing x in this equation equal to a gives you something else as well too. So let's say I change some things up on you. Let's say now we're going from a to a, all right, of f of t dt. This would equal f of a plus c, right? Our upper bound, a plus c. However, we know that a lower bound and an upper bound meeting together at the same thing should equal 0 in the end. And so what this tells us is that 0 should equal the antiderivative of a plus c giving us a value of c being negative f of a. Why is this important? Because the value for c now is not plus c anymore of our original integral. The value of c from a to x of f of t dt can kind of sum up everything as the antiderivative of f of x minus the antiderivative of a. All right? So it's basically, can you find the antiderivative of f? You have your upper bound x minus your lower bound a. All right? Your upper bound x minus your lower bound a. Let's do an example and kind of put all the pieces together. All right? We want to find the integral from 0 to pi of a basic function sine of x. Just can we identify a little bit more so here? So remember what the integral is, okay? We're trying to find what was basically the step before sine of x happening. Well, if my derivative was sine, that means my function itself had to have been cosine. But hold on, we know the derivative of cosine to be negative sine. So that means if my derivative ended up in positive sign, that means that before that should have been a negative cosine, so the negative and negatives would have canceled on out, and we would have gotten a positive value in return. So to evaluate this becomes negative cosine of our upper limit pi minus negative cosine of our lower limit 0. Well, we see that this is negative 1 minus a negative 1, because cosine of 0 is 1, negative 1. Boom, there you go. And putting the pieces together, negative, makes positive. This has a value of 2. So, ladies and gentlemen, we have, in my opinion, truly just really evaluated our first antiderivative here. Has a value of 2. All right. So, let's take a look at, again, I want to give you one basic one to kind of give a shot on your own here. And that is going to be to evaluate from 0 to 1 of e to the x dx. All right. And once again, I want you to evaluate this integral. And your end result should end up with e minus 1. So that should be your answer. Give it a shot. See if you come up with that result. And we'll go over it first.